Now let's take a look at the Poisson probability distribution. In experiments or sampling where we are interested in counting the number of times some event occurs during a specified interval, and the interval may be time, distance, area, or volume, the random value will follow the Poisson probability distribution. So we observe two assumptions when using the Poisson probability distribution. One is that the probability is proportional to the length of the interval, and two, the intervals are independent. Here are some examples of variables that may follow the Poisson distribution: the number of misspelled words per page in a newspaper, the number of calls per hour received by Dyson Vacuum Cleaner Company, the number of vehicles sold per day at Hyatt Buick GMC in Durham, North Carolina, and the number of goals scored in a college soccer game. So now let's talk about how to compute the probability of a certain random variable x for a Poisson distribution. Since we know the value of the random number for which we want to obtain the probability, and we also know the value of e, we only need to know the mean, mu, of the population. A later slide will demonstrate how the Poisson formula is used to find the probability for a random number x given a population mean. The mean number of successes, mu, can be determined in Poisson situations by multiplying the sample size n by the probability of success pi. The variance of the Poisson distribution is also equal to the product of n and pi. So in other words, the variance of a Poisson distribution is equal to its mean, mu. So let's look at an example using the Poisson probability distribution. Assume that a baggage is rarely lost by Northeast Airlines. Suppose a random sample of 1,000 flights shows 300 lost bags. What is the probability that no bag will be lost on a flight? So this situation follows the Poisson distribution since we are counting the number of bags lost per 1,000 flights. So to solve the probability, we'll need to find the arithmetic mean number of lost bags per flight. This is obtained by dividing 300 by 1,000, which is equal to 0.3 lost bags per flight. We then use the Poisson formula to compute the probability as shown on this slide. So the probability that none of the bags is lost is 0.7408 or 74.1%. Another method is to use table 6.6 by locating the intersection of x equals 0 and the average lost bags per flight, mu equals 0.3. So on the next slide, we're going to see an illustration on how to use the Poisson table. In either case, the probability of not losing a bag on the flight is 0.7408. On this slide, we show the method for using Appendix B.5 to find a Poisson probability. A portion of the Appendix Table B5 is shown here. In using a Poisson probability table, what we need is to locate the value of the mean of the distribution. In this case, the mean is 0.3. The 0.3 column on the table is highlighted. We then locate the value of the random number. In this case, x equals 0, since we are interested in finding that no bags will be lost on a particular flight. So the intersection of x equals 0 and mu equals 0.3 is 0.7408, and this represents the probability that no bags will be lost on a particular flight. So while the use of this table is convenient, many Poisson tables are not exhaustive enough to include all of the many values for mu. It's therefore good to know how to use the formula that we talked about in the previous slide. So now let's talk a little bit more about the Poisson probability distribution. What's the shape of the Poisson distribution, and how does its shape change when the mean increases? So the figure in this slide shows the shape of the Poisson probability distribution. It's always positively skewed, and the random variable has no specific upper limit. So look, however, note that as the mean becomes larger, the Poisson distribution becomes more symmetrical. So you can see here, as it gets bigger, it's getting more symmetrical or bell-shaped.